Hello, everybody, and welcome to this deep dive seminar on the lead article published in Frontiers in Science, Emerging Signals of Climate Change from the Equator to the Poles, New Insights into a Warming World. I am Laure Sonnier. I am the executive editor of Frontiers in Science, and I'm very excited about today's event. This project is actually the result of a collaboration between so many experts, some of whom are with us today. So a big thank you to all of you for being such a brilliant panel, and a very special thank to Professor Mat Collins for your trust and leadership in bringing this important project to completion and success. Indeed, for so many reasons today, not even touching on politics here actually, it is critical to improve regional climate science, to better understand regional and local impacts, and to develop effective adaptation measures and policies, truly addressing people's urgent need. Just in the past few months, we have seen already record-breaking climate events, such as Hurricane Helen in the US, the strongest hurricane ever recorded in Florida, or the devastating floods in the Valencia region of Spain. So at Frontiers, we really truly believe that we need to accelerate transformational science accessible to all. And this is exactly what we are especially doing at Frontiers in Science. So just a few words about Frontiers in Science. This is Frontiers' flagship journal, and we launched it over 18 months ago. It's a multidisciplinary open access title. It focuses on the science that can accelerate the solution we need most for healthy lives on a healthy planet. So how do we do it? We do commission exceptional peer-reviewed lead articles from internationally renowned researchers whose work addresses global challenges in human and planetary health. Then, around each of these articles, we built a hub of multi-audience content, which includes viewpoints, editorials, policy articles, and also content for children and for the general public. So this is all designed to extend the journal's reach across science, policy, and society. And as of today, no other publisher is doing this in the way we do. And we are very proud to be actually driving innovation in publishing so that exceptional science, your exceptional science, can actually reach everyone in society and accelerate progress for all. These days, we are celebrating at Frontiers in Science, after 18 months of existence, our 15th article hubs published, over 800,000 views of our articles, more than 120,000 downloads, and already over 250 citations. So I'm sure you will agree that this is quite a testimony to the success and to the impact of our still quite young journal. And there are many more important publications to come. You'll hear about them at the end of this webinar, so stay tuned for more on this. But today's expert scientific discussion will be moderated by Rui Fernandes, one of our amazing content editors in the editorial team at Frontiers in Science, and also an ecological modeler by research background. I'm delighted to hand you over to him now. Thank you all. Enjoy the event, and a huge welcome to everyone, the speakers, the panelists, and also our online audience. Thank you very much.
Thank you, Laure, and hello to everybody around the world. Good morning, good afternoon, and good evening, wherever you are. As Laure mentioned in her introduction, this deep dive focuses on the Frontiers in Science lead article, titled Emerging Signals of Climate Change from the Equator to the Poles, New Insights into a Warming World. It was published in October 2024 and led by Professor Mat Collins. The impacts of climate change are becoming increasingly clear. More severe storms, changes to rainfall, prolonged and more extreme heat waves, and rising sea levels, to name a few. With the effects of the warming climate are felt globally, accurate information about regional impacts is critical to help communities prepare for the specific climate hazards they face. In their lead article, Mat Collins and his co-authors present new insights into how climate change is affecting different regions of the globe across different latitudes. The authors reveal emerging patterns of severe weather events and environmental changes that pose significant risks to both human and natural systems, affecting everything from infrastructure and public health to economic stability and food security. The lead article and the complementary publications in this article hub also calls for deeper assessments of regional climate risks and vulnerability to better inform climate policy and adaptation measures by governments, citizens, and businesses. This is the article hub. It includes an editorial by Professor David Frame of the University of Edinburgh in New Zealand, and viewpoint articles by Professor Shang-Ping Xie of the University of California, San Diego from the United States, and Professor Swadhin Behera from the Agency for Marine Earth Science and Technology in Japan, both of whom join us today. There is also a lane explainer, infographics, and video, as well as an article in Frontiers in Young Minds, our journal for kids. To start off today's agenda, we will begin with Professor Mat Collins, who will set the scene for today's discussion with an initial deep dive into the lead article. He will then be followed by Professor Gabriele Hegerl from the University of Edinburgh. Finally, we will have a panel discussion and a Q&A session with both speakers and some of the contributors to the article hub, Professor Shang-Ping Xie and Professor Swadhin Behera. So now let's turn our attention to our first speaker. Professor Mat Collins is a distinguished climate scientist and the Joint Met Office Chair in Climate Change at the University of Exeter in the UK, specializing in the physical science of climate and climate change, particularly in the areas of climate variability, El Niño, monsoons, and atmosphere-ocean interactions. His work with complex climate models is helping to refine predictions of future climate conditions and improve climate resilience. Matt has played a key role as a coordinating lead author in the Intergovernmental Panel on Climate Change, or IPCC, the fifth assessment report, and the IPCC special report on the ocean and cryosphere in the changing climate, which are crucial for informing global climate policy. His expertise extends to advising significant environmental initiatives, including the Royal Commission on Environmental Pollution Adaptation report, the UK Climate Change Committee, and the Stern Review on the Economics of Climate Change. In recognition of his impactful research, Matt was listed among the top 2% of the most cited scientists globally in 2020. Matt, thank you very much for bringing this article to Frontiers in Science, and the floor is yours.
Thank you, Rui, and welcome everyone to this discussion about our paper. I see a few names of friends in the webinar chat, so hi to you. What this paper is a selection of interesting new results about regional climate change. It's arisen out of a couple of projects that we had in the UK that was funded by, they were both funded by the Natural Environment Research Council. What unfortunately it is not is a synthesis of all the things that you could learn about regional climate change. This is a vast topic. We couldn't include everything. If you're interested in reading more about regional climate change, you need to get one of these, which is one of these IPCC reports. So you can see that from the article that you can access online, we couldn't cover everything, but we hope there's something here for all of you. Okay, so I'm going to start with some basic framing and explanation of how we do our work on regional climate change. Some of this may be known to many of you, but I hope it's useful to set the context for perhaps those who are joining who are not regional climate change scientists. So we use, because we don't have observations of the future, we use global climate models and regional climate models to project forward in time what we think will happen in the climate system. These global climate models are complex numerical codes. They're solving the fluid dynamical equations of the atmosphere and the ocean on a horizontal and vertical grid. And within the little grid boxes, we have to represent processes which cannot be simulated on the grid, so things like clouds and rainfall and snow, the transfer of heat and momentum between the ocean and the atmosphere, but not shown on this graph, but biological processes, etc., etc. So these codes are typically up to 1 million lines, and they take many days and months to run these simulations on the world's biggest high-performance computing facilities. What we do in our subject is to gather together information from many different climate models and share it, so we can all look at the model output. We can all look at these different projections of climate change. So I'm going to start here with a sort of global mean picture. So what we see on the graph here in the top left, the grey lines are individual models, and these are representations of the global mean surface air temperature with respect to some climatological period, here 1850 to 1900. So they're what we call anomalies. They're changes with respect to that time period. And they all show, the x-axis is the year. They all show simulations from 1850 through to the present day, and then into the future. Now, all the models show a global warming in the historical period and in the future period. And we know that from other studies that this global warming is caused by increases in greenhouse gases, but that warming caused by the increases in greenhouse gases is actually offset by some cooling from sulfate aerosols. So there's a balance between the warming effect of CO2 and the cooling effect of pollution. And that becomes important when we start looking at regional climate change as well. What we also know is that as we go into the future, there's a spread in the simulations, and also that we know that not all models are perfect in terms of their reproduction of the present day climate. The white line on the graph shows the observed global mean temperature from 1850 to the present day. And you can see that models in this case, or the average of the models in the red curve, is slightly warmer than that white curve. So what my colleagues have done in this particular study is to adjust the models down. So we think the models are running a bit hot. And that's something that we do also in the regional climate case. We have to make sense of the spread in the simulations, any discrepancies between the model and the observed climate, and we have to put all that together with our understanding of how the climate system works, using statistical and dynamical techniques, and sometimes even now machine learning techniques, to make a kind of best estimate of what we think will happen to regional climate change. So you need to bear that in mind when we talk about what's happening under regional climate change. You know, there's always some kind of uncertainty. The reason it matters is that in this bottom panel, we're looking at the probability of exceeding 2 degrees warming in this case. So this is one of the Paris targets. And you see that the probability rapidly rises from about now to almost certainty by 2060 if you use the raw model output. But if you use this adjusted down, we buy a little more time in terms of the efforts that we have to make to reduce greenhouse gases, to limit the effects of global warming, and to avoid these crossing these target points. For the future, of course, we don't know what the world will be like in terms of the amount of greenhouse gases in the atmosphere, and also these aerosol particles. So we use these scenarios. So this is a really complex kind of component of climate change science, is trying to project forward what the world will be like in the next 100 years or so. And so we use this concept of scenarios from, a highly sustainable world up to a world in which we basically business as usual, carry on emitting. Currently the science says we're maybe in the middle of these, but you know, there's a lot of uncertainty here. And in some of the work that we've looked at in this synthesis paper, we look at the difference between scenarios and how that matters. And one more thing to say before we get on to the regional studies is one more thing to say about the global mean picture is that global warming will continue even after we reach net zero. So there's efforts to reduce emissions of greenhouse gases, you know, particularly CO2, to zero at some point in the future. Even if we do that, there may be some warming beyond that, but you know, we'll be stuck with some climate change that with respect to the kind of pre-industrial period. These are actually runs in which the concentrations of greenhouse gases are fixed, not the emissions turn to zero. So for the experts, we would expect a kind of leveling off of these curves if we had a zero emission type of scenario. And indeed, there was a Frontiers deep dive a few months ago looking at this concept of the zero emission commitment. So you can go back over the YouTube channel, I'm sure, and see that one again. But the message is, you know, climate change is here to stay, even if we reach net zero. So we're probably going to have to adapt to things, the climate change that we're seeing now, of course. So now to go into a few regional components of climate change. So the first topic is monsoons. So what are monsoons? Well, one way of thinking about them is the seasonal migration of intense rainfall bands from the over the ocean to over the land. So this happens in many parts of the Northern Hemisphere in summer. So in West Africa, in South Asia, in East Asia, Southeast Asia. And these, of course, are really important for agriculture, and also really important because they can bring floods and other hazards. So if we look at some climate model output, so what we see on the left here is change in temperature. So now we're looking at a geographical pattern of temperature in the tropics under a low emission scenario and under a medium emission scenario. So the first thing you note is that, in fact, the land warms more than the ocean. So this is a well understood phenomena. So it means, in fact, if we're talking about a 1.5 or a 2 degree temperature rise, we're really talking about more warming over the land than 1.5 or 2 degrees. In this higher scenario, the land warms more. And what this pattern, together with the fact that a warmer atmosphere can hold more moisture, or strictly speaking, the saturation water vapor in a warmer atmosphere is higher. What we see in both of these even the low emission scenarios and the medium emission scenarios, is increases in rainfall in West Africa, in South Asia, Southeast Asia, and East Asia. So the main monsoon regions all are intensifying in the future. They intensify more under the higher emission scenarios. So the temperature is proportional, the rainfall is proportional, rainfall change is proportional to the temperature change. And a key point, which was not actually represented in that figure, the first bit is that the monsoons are expected to increase in intensity in the future. Now, we haven't really observed this in the observations, and that's because there's this fight again between the greenhouse gases and the aerosols. So the greenhouse gases are tending to push up the rainfall, the aerosol emissions are tending to decrease it. And there's an approximate cancellation, which means that you don't see much of a trend in these monsoon regions in the historical period. But we expect in the future, as the greenhouse gas concentrations get even bigger and the aerosol emissions actually are abating, because we're cleaning up power stations, which is good for air quality. That the greenhouse gas signal will win out, and we'll see increases in these in this monsoon rainfall. The next feature I want to talk about is another sort of tropical phenomena. It's the El Nino Southern Oscillation. So this is a big reorganization of the sea surface temperatures and rainfall in the tropical Pacific. Happens naturally, periodically. We had an El Nino event in 2023, and it's tailed off at the beginning of this year. Wasn't a particularly strong event. But what we looked at in this study was when might we be seeing changes in the El Nino in the future based on our climate model simulations. So, perhaps if we just look at the graph on the right here, this shows something called the time of emergence of the signal in the rainfall response, the sort of rainfall metric of El Nino ENSO variability. And we see that we expect to see the emergence of that signal around 2040. So, you know, in not so many years. In fact, there's a big uncertainty bound around that. But because we have multiple versions of these models, we can extract the signal. One of the interesting and unexpected things that we saw in this study was that looking at the different scenarios, it didn't make much difference what scenario on. The signal still emerges around 2040. So this might be one of these phenomena in the climate system that cannot be avoided. So no matter how much mitigation we do, we might still see these changes in El Nino in the next 15, 20 years. There are a number of caveats around that, I should add, particularly because we don't understand fully what's happening in the real world, in the tropical Pacific, in terms of SST patterns. And of course, there's a lot of natural variability, but this is just one of these kind of studies that one can do with these climate models these days. We know that remote regions of the world do not have independent climates, if you like. There are connections between them, what's something that we call teleconnections. Here on the left-hand side is it's in fact a change of a known teleconnection. So during El Nino events, North America and Canada are generally warmer and actually wetter than normal. In our model projections, we see that there's a reduction in strength of that teleconnection. So the teleconnection to North America weakens. And that is shown in the majority of these different climate models. And we can understand that in terms of the dynamics of the atmosphere. And it turns out to be related to the shift in rainfall, which is actually responsible for the early emergence we saw on the previous graph. So the El Nino events are moving into the East Pacific and becoming more extreme by that rainfall measure. There are, of course, many other teleconnections in the world, and we're only beginning really to understand the influence of climate change on some of these connections. Moving to mid-latitudes, so changes in storms. So in mid-latitudes, the climate is, I'm sure those of you who live there, dominated by storm events, which come frequently across ocean basins. Here in the UK, we experience storms that come across the Atlantic. In this study, we were looking at very high resolution climate models. So the grid is very fine. And what we see in this study is that in the Atlantic, there's something called the Gulf Stream. And in the real world, that has been observed to move closer to the coast of the east coast of the US. So it's changing its location. Previously, our low resolution models shown in the green didn't pick this up. But the high resolution models, in this case, high resolution in the ocean component, in which you can simulate some of the very fine scale details of eddies, show this change in location of the Gulf Stream. And why is that important? Because the air which is coming across, steered by the Rockies, it's very cold air which comes off the US East Coast. It's cold air coming over a very warm ocean, and that is where all these storms are generated. So there's a big instability, and this is the birthplace of the storms that come across the Atlantic storm track and affect us in Western Europe and in the UK. And if you change the location of the Gulf Stream, then in fact it amplifies this generation mechanism, and those storms come across the Atlantic, and we see the amplification. So we see a regional amplification of storms as a result of this shift in the Gulf Stream in the very high resolution models that we don't see in the low resolution models. Finally, before I hand over to Gabby, one other thing that we looked at was in the very polar regions of the planet. And a new result here is that there's a lot of obviously usually snowfall over the Arctic and the Antarctic. This is really important for maintaining the ice sheets in Antarctica and in Greenland. But we see, because of the warming of the planet, that snowfall is more frequently falling as rain. Now, this has a feedback. If it's falling as rain, it can run off. It can change the reflectivity of the surface such that more energy from the sun is absorbed, and it could potentially destabilize some of these ice sheets. If these ice sheets get destabilized, we could see very rapid sea level rise. That is a kind of whistle-stop tour of some of the key messages of the paper. And next, I'm going to hand over to Gabby, who's going to take us through the work on extremes.
Thank you, Matt, for this important overview and of the key messages on your lead article. And just a reminder to our audience before we pass on to Gabby, if you have any questions about what is being presented here today, please make sure to add them to the Q&A chat, so that we can answer them during the Q&A session. So as Matt said, our next speaker is Professor Gabriele Hegerl from the University of Edinburgh. Gabby is a distinguished climatologist and holds the personal chair in climate system science at the School of Geosciences in the University of Edinburgh in the UK. Her research primarily focuses on the causes of climate change and the impacts of extreme weather events. And her work has been instrumental in the detection and attribution of anthropogenic climate change, significantly advancing international climate policy. Gabby is a co-leader of the World Climate Research Program, Safe Landing Climates Initiative, and has co-led their Grand Challenge on Extremes, and as a coordinating lead author of the IPCC Fourth Assessment Report. Her contributions have been crucial in understanding global climate dynamics. Gabby, thank you very much for being here. The floor is yours.
Thank you, everybody, and nice to see you. So extremes are a huge topic. So I'm going to not touch on all extremes, but will focus largely on heat waves, because those alone give us enough to talk about. And Matt has touched on some of the other extreme events. So I want to highlight a few aspects of recent extreme events that show that there is still a lot left to understand, and that extreme events can surprise us. The first one is the level of extremeness of some of the events we have observed. So this is now here looking at the Pacific Northwest heat wave in 2021, and the top left diagram shows the temperature, the daily maximum temperature on average over Alberta, plotted against global mean surface temperature. And you can see that there is a little trend, some trend in the data points, but the the turquoise data point at the very top of the screen is the one of the 2021 heat wave, and you can see a really record-shattering event that is very different from the typical records in that time series, or record heat days in Alberta in that time series. And in the paper that this is drawn from by Vicky Thompson, she fitted a general extreme value distribution to the records, the annual records before, which would be the way where we used to anticipate what is a very rare event. And you can see that if you do that, you wouldn't anticipate an event as strong as the one observed. Whereas in contrast, if you use the second hottest event, there is no problem reproducing this. So these record shattering events are really surprising. They also occur in climate models, so they are not something that challenges in the sense of modeling them, but they are challenging statistically to when we try to anticipate what is the return period of extreme events, because you couldn't really well estimate it based on past events. There's a few statistical complications about using the general extreme value distribution like this, which I won't go into, but it is it would be quite tricky to anticipate the strongest events where the feedbacks for example, of the land surface change, and where you see an event that is much stronger than what has happened before. And so a point that Vicky in her paper highlights is that if you have a region that hasn't recently experienced a particularly severe extreme event, you might actually be quite surprised by the events that occur. This has been observed a little bit over Europe, where the 2003 heat wave was a real surprise and very extreme, with huge consequences, and subsequent hotter heat waves have caused less consequences than this very first wake-up call heat wave. And the plot at the bottom, I would like you to focus on the bottom plot, highlights in red where we have seen very exceptional heat waves recently that were statistically surprising. And in contrast are regions where you have light blue colors, where the current records return period is not particularly extreme. And you could argue that these regions are might be surprised by when one of these whopping extremes comes along. So that could be relevant for preparedness. The second aspect I would like us to focus on is to what extent are we actually able to predict how heat waves change. And there is a nice paper by Gerd Jan von Oldenburg, which was his last paper published posthumously, that focuses on all the aspects we don't understand about heat waves and hot extremes yet. And this is a paper by a master student of mine, where we looked at changes in the distribution of extreme heat over the planet and with increasing warming. And we have highlighted on some regions where we are not just expecting a shift of the distribution with warmer temperatures and everything else stays the same, but where we expect interesting changes. So, for example, when you look at the Svalbard region, in the climate models, when you look at these fitted distributions, that blue is the present day climatology of the hottest day in a year, green is 1.5 degrees, orange is 2, and red is 4 degrees, is 3 degrees, oops, I think. Then you can see that in some of the distributions that you see from different large ensembles of climate models, you can see that the ratio of the peak relative to the other periods changes. So, for example, with the IPSL model, you see a much steeper and narrower distribution, which could be connected to the sea ice around Svalbard in the future, which is much less in the summer, and so you could experience less wide distributions. On the other hand, you can see over regions like the Amazon region or also Central Europe that in some of the models the distribution gets wider, so the peak gets shorter compared to the long tails, and that you see that particularly with the Max Planck model here, where you have, as we go to the warmest climate, 3 degrees, you can see a much longer tail compared to the beginning of the simulation. So you could already anticipate from the way these curves are so different between the different climate models used here, so that we have several large ensembles, CANISM, IPSL, Max Planck low and high resolution, relative high resolution at the time. And you can see how different these distributions are. So they can't possibly all be right. And if you look at the comparison of the present day hottest day in a year in the climate models compared to in gray histograms, the reanalysis observations or reanalysis, which is close to observation, you can see that we are very much off the chart in many regions. So, for example, Svalbard is already warmer than all of the models expect. On the for the Amazon, only one of the models has a reasonably narrow distribution, similar to the one that's observed over this box in the Amazon by the reanalysis data. Central Europe, and that was one of the focuses also of Gert-Jan's paper, is experiencing hotter heat waves than expected at the present time. So none of the models anticipates this. So we could argue that not only is there an uncertainty in the behavior of the models with how much hotter the hottest heat wave gets, and to what extent the distribution of a hot day changes as we go into a hotter climate, but there's also we can't even do the present day heat climatology very well. So there is a bit of an information deficit and still needs to model better. And it could be that the high resolution models Matt mentioned help us a bit here, but it is not necessarily clear that this will be the case. It remains to be seen. And that paper is, this plot is from a different paper where we have looked at, where Nico Freschi has looked at to what extent models that have a better climatology of hot days change differently in the future. So this is now looking at the frequency of heat waves. And on the left-hand side, you see how the frequency of heat waves exceeding the 98th percentile changes in a warmer world of 2 and 1.5 degrees. And you can see that you see a particularly strong change in the tropics, where the temperature distribution is narrow and where it is easier for the global warming signal to emerge out of the variability. And that is quite a theme in hot extremes, is that the narrower distribution in some regions in the tropics means that they are faster to be seen relative to variability, and which could lead to larger impacts. But if you go on the right-hand side, if you pick from those models, the models that have a reasonably accurate width of the temperature distribution at the hot end, and I could now go in great detail of how this has been determined, then the frequency of these hot days gets almost twice as much in many of the regions which have been evaluated. A simple explanation that is not that could be close to what's happening for some models, but it needs to be looked at more, is that many of the models dry out too much at already present day climate, and then the tail is already quite wide, and so as we warm more, the change is not as large as for those models that may be more realistic, that they keep that make it still quite hard to dry out the land surface. So the land surface is probably a big factor here, and it will be interesting to see to what extent high resolution models that Matthew talked about are different. There is some papers indicating that the land surface does behave differently if you have a much better resolution. So this is all a bit academic to what extent heat waves exactly change. But when we think about the consequences of heat waves, we should also think about health and how heat is dangerous for humans. So it's not only that hot events become more frequent and more intense by a little bit, which doesn't sound very problematic. But if we look at heat indices that indicate to what extent humid heat is occurring, then you see an emergence of quite problematic humid heat events. Humid heat is more dangerous for humans than dry heat in many places, although there is a bit of a discussion what exactly is the most dangerous heat for humans. So we have used here the wet bulb temperature, which is basically you wrap your thermometer in a wet cloth, and then you get an indication of how hot it feels for somebody who is sweating as much as they can. And so at the reference period, and humid heat of about 31 degrees is considered dangerous. Wet bulb of 31 degrees is considered dangerous, and 35 deadly, or if you're with prolonged outside exposure. And with the relatively coarse resolution models used in this study, you see at the present time, a reference time period, only in a very limited area in the Gulf of Aden, some dangerous humid heat, but then there's, with a better resolution in modeling, you would expect a little bit more of those in around coasts. That is not well resolved in these simpler models. But as you go to 1.5, 2, and 3 degrees, you see that initially rarely and then increasingly more frequently, indicated by the yellower tones, you get more of these dangerous greater 31 degrees humid heat events across the globe, particularly in India, Australia, parts of the humid parts of Asia, Africa, and South America. So quite a dramatic increase in temperatures that are threatening to humans if working outdoors. And you could also look at this from a population perspective. So this is the same plot, again, for the wet bulb temperature on the left that we have seen here before, but is now expressed in terms of exposure in percentages. So the population projections are folded in with the exceedances, and you can see that as we go into a warmer world, this dangerous heat is experienced by many more people, particularly around India and East Asia. And if you use a different indicator of dangerous humid heat, as indicated in the middle and right column, the difference is not particularly large. It's a very robust picture to how exactly you measure humid heat. So we go into a region where the hot extremes are not just increasing, but they are becoming dangerous because they breach thresholds. So we also see an emergence of consequences of extreme heat. This is looking at the Arctic now, north of 60. On the left top is the Canadian Arctic, an American Arctic, right is the Siberian Arctic, largely. Bottom is around Greenland, and then below is the Scandinavian and West Russian Arctic. And in red are is the percent of grid cells that have vegetation that are exposed to a strong heat wave, or to a cluster of extreme heat. The clusters have been identified by some AI method, which was fun to do with the master student, and you can see that there is, in some regions, there's a lot of variability in the Canadian Arctic, where in some regions you see already a strong emerging trend, and Arctic-wide there is a positive trend, of course, in the incidence of summer heat waves. But if you look at the white bars, these are the burned area per total burnable area, and you can see that the percentage of burnt area correlates very, very much with the incidence of extreme heat waves, these large-scale heat waves. And so we see an increasing incidence of fire as we have a stronger heat wave climate, which has consequences, for example, carbon release, but also the air quality. Some of the Canadian fires, for example, have really had huge impacts also on North American air quality. And so this emerges into some priorities, I think, what we need to do more of. So first off, we need to get a reliable estimate of the changing hazard of extremes for adaptation. And I've tried to make the point that for heat waves, we are not there yet, and the heat waves are maybe the most straightforward extreme event, and so it's even trickier for rainfall extremes, which are more affected by circulation changes. But we also need to consider the vulnerability and exposure of populations, which you have seen with the humid heat exposure maps, where these events are particularly impactful, where you have a large population. The fire and vegetation response to extremes, such as vegetation stress and dieback, is really important for the carbon cycle, but it can also feed back on the climate by changing the land surface. So if your forest doesn't come back or tips into a different climate, into a different vegetation, you have a feedback on the heat wave climatology and on generally the extremes climatology, or you change the ability of the land surface to recycle moisture, and also you release carbon, which and the carbon released by some of the recent large fires have been very important and have and are for example, for the Californian fires in a similar order of magnitude as as California's traffic emissions. So it is an important concern also for carbon cycle and for to what extent the land surface continues sucking up carbon. And we need to think about the consequences, the downstream consequences of extreme events. And their links to near-term and irreversible or rapid change. So there's even for some of the tipping points of concern, there is links to extreme events, and we need to better understand this, and we also need to better understand to what extent actually irreversible changes occur, and to what extent the large multidimensional climate system is more or less resilient than the simple models that warn of tipping points. Thank you.
Thank you, Gabi, and thank you, Matt, once again for setting the scene for today's discussion. Now we're going to discuss some of the issues raised by Matt and Gabi with our guest panelists. So we will soon be taking questions from the audience. So please, once again, make sure that you leave your questions in the Q&A chat. But first, I would like to welcome our guest panelists. Professor Swadhin Behera is the director of the Application Laboratory at the Japan Agency for Marine Earth Science and Technology. He is a renowned expert in global ocean and climate research, recognized for discovering key climate variations such as the Indian Ocean Dipole and the Indian Ocean Subtropical Dipole. Professor Behera led the European-Japan collaborative project to develop the Syntax Frontier Coupled General Circulation Model on the Earth Simulator, which is a cutting-edge model for climate predictions on seasonal to decadal scales, whose predictions are integral to outreach programs aimed at societal benefits. Swadhin is an active member of key professional societies, including the American Geophysical Union, the Japanese Oceanography Society, and the Japan Geoscience Union, reflecting his significant contribution to the field. Professor Shang-Ping Xie is a distinguished professor of climate science and the inaugural Roger Revelle Chair at the Scripps Institution of Oceanography in the University of California, San Diego. Shang-Ping's research focuses on ocean-atmosphere interactions and their impact on climate formation and variability. He is renowned for formulating the wind evaporation sea surface temperature feedback mechanism, the Indian Ocean capacitor effect, and the warmer get wetter concept for rainfall changes due to global warming. His discoveries include what Science magazine called the world's longest highland wake. He is also the lead author of the IPCC Fifth Assessment Report. His work has significantly contributed to climate science, and his achievements have earned him numerous honors, including the Sverdrup Gold Medal, the Meteorological Society of Japan Medal, and the National Science Foundation Special Creativity Award. Professor Xie is a fellow of both the American Geophysical Union and the American Meteorological Society. Welcome, Shang-Ping and Swadhin, and thank you for being part of this event today. And for us to get today's discussion going, I will start with our guest panelists, and my first question is to you, Swadhin, on the topic of enhancing climate model accuracy. In your viewpoint of on the lead article, you highlight uncertainties in climate model projections, especially concerning critical thresholds like the 1.5 to 2 degrees Celsius targets. Could you elaborate how you and your colleagues at the Japan Agency for Marine Earth Science and Technology are advancing climate modeling techniques to improve the accuracy of these projections? And more specifically, what innovations are being used to understand variables such as climate sensitivity and feedback processes?
Thank you, Rui, and hello, everybody. It's quite late in Tokyo. Thank you for the question. Yes, as we heard from the previous two speakers, we have various things going on like improving model resolution, improving model parameterizations, physical parameterizations, so that we can represent cloud, albedo, aerosols well, and their feedback well. At Jamstack, we have several groups working on different models. In my group, we are working on the syntax frontier model, which you introduced while introducing me. And that model is mostly for the present day climate and mostly focusing on seasonal to decadal predictions. But there's another group which is involved together with University of Tokyo to develop one of the IPCC models called MIROC. And that model, they have been developing for last 20 years. And in that model, they have been doing most of the things which Matt and Gabe already touched in their talks, especially improving the resolution and also trying to improve the representation of extreme events, the persistent droughts, the floods, and also I think something is going to touch on that later, the atmospheric river, which is affecting the rainfall over Japan quite intensely nowadays. And that we feel might be contributing to the sensitivity of the models for these target 1.5 degrees or 2 degrees centigrade. So there are many things happening in that group. They have been trying to improve the physical processes, improve the resolution of that model. And also they are trying to improve the ecosystem model, what they have, like introducing the dynamical vegetation, and also improving the biogeochemistry in the ocean model, including how the physical, the mixing is happening in the upper ocean. We are doing the same thing in our group also to kind of improve the prediction of the present climate. Matt touched on El Nino, the monsoon, the regional climate, and they are also very important for the model sensitivity. And we have been doing for that for the present climate, but we have an aim so that this kind of present understanding can be projected into the future to improve our understanding on model sensitivity and how well we can represent the present climate in the future climate, especially the frequency of El Ninos, the intensity of the El Nino, and the spectrum of the El Nino. Some of the El Ninos we see they emerge quickly and then last longer. And some of the El Ninos, they slowly grow and then quickly decay. And those kind of El Ninos are happening nowadays. And we want to understand why those are happening, because we have challenges in predicting those emergence of El Nino signal and the decay of the El Nino signals for the predictability on seasonal to interannual time scales. Besides that, of course, most of the models have trouble to capture the monsoons. And we are trying to understand that, especially because monsoon has not only the effect, the direct effect on the regions that are experiencing the monsoon, but because of the diabatic heating, and they also teleconnect to other regions. So we need to understand why some of the models are doing slightly better than the other models. And then how do we improve those biases? And Matt touched on the AI machine learning. And we are also doing that both for the projections and the predictions to improve the data assimilation, the data going into the models, the physical parameters to pick up the best parameters for fine tuning and also the physical processes, and also improving the model ensemble mean by using machine learning, the process in which we try to get the best prediction of projections from the number of ensemble members. So those are the ways I think we are trying to improve our models, both for present climate and also future climate. I'll stop there. Thank you.
Great. Thanks, Swadhin. and for those insights in your work and a very detailed answer. It's like you really learn a lot already, like in this 5 minutes. So thank you. So now over to you, Shang-Ping. I would like to start by discussing the topic of the coupled feedback mechanisms. So in your viewpoint, you emphasize the significance of the coupled ocean atmospheric feedback in shaping regional climate patterns. How are you and your colleagues at the Scripps Institution of Oceanography leveraging this understanding to enhance the projections of the El Niño's Southern Oscillation related climate impacts, especially in regions like the southwestern United States? And what do you think are the key challenges that you are facing in your research?
Yeah, thank you very much for the opportunity to participate in this event. Yeah, so I think ocean basically is has a lot of heat inertia, therefore it's an important pacemaker, not only for the global mean surface temperature, but also for how the El Nino is going to change. So I think Dr. Behera has discussed in detail how to evaluate El Nino simulation of El Nino in climate models. And I would like to kind of emphasize, there are a lot of extreme events around the world that can be related to, we believe are induced by El Nino Southern Oscillation. So that we kind of want to kind of analyze or predict the current events, and therefore, in the process, learn the climate system better. And then, with regard to El Nino change in warming climate, I guess Matt mentioned, there's a tendency for models to produce El Nino Southern Oscillation that's going to intensify in warming climate. So that our study kind of confirmed that, but also we saw there's inflection point, in other words, and so kind of intensifies for the next few decades, and then in the later part of 21st century, if we keep increasing atmosphere concentrations of carbon dioxide, we saw the ENSO is going to turn on a kind of a downward trajectory. So there's a lot of details with regard to why and why this happened and so on. But my point is, the climate system is quite complex, and especially when we consider the coupled ocean atmosphere as a system. So like ENSO could behave not in a non-monotonical fashion. So that kind of increase the complexity. So I'm just going to stop here, to see what the audience has to.
Great. Yeah. Thank you, Shang-Ping, for your answer. And great. So we are now opening the floor to some questions from our live audience, and we have already some questions coming out, and that we have here ready for the panelists. So I'll jump in just right to the first question that comes from Tom Chowlerton. I'm sorry if I'm saying the name wrong, but it's for Matt first, and then anybody can jump in. Matt, what do you think are the uncertainties in warnings associated with the range of emission scenarios?
Hi, Tom. Well, of course, the emission scenarios point is a very tricky one, because it's difficult. We're looking into the future with our models, but we're trying to, with the scenarios, look into the future of the socioeconomic state of the globe, which I think to me is a much harder problem than doing climate. I guess what you might be referring to is the state of play with respect to aerosol forcing. So I think most of the scenarios actually assume that there will be a quite rapid cleanup of the atmosphere in terms of aerosol distributions, and that assumes that everyone gets their act together and closes down all their coal-fired power stations, etc., etc. Maybe that won't happen, and maybe that's not even equitable. So I think there's still a huge amount of uncertainty, in particular about the future scenarios. Maybe we've honed down the greenhouse gas uncertainty a bit with the whole COP process, but certainly there's still a big uncertainty there.
Okay, great, thank you. I don't know if anybody else wants to jump in, but feel free to let us know while we are at the discussion. Otherwise, I'll just jump in right to the next question, which comes from Bin Yu. I'll start with this one because it was posted also in the chat, the general chat. So thanks, Gabby. Binu says, thanks, Gabby, for the interesting results. Regarding the extreme heat waves in different regions, generally speaking, to what extent do these extreme events occur at the same time? So some examples connected through large-scale teleconnections, as discussed in recent studies. And also, are they expected to appear simultaneously in the future?
That's a great question and a big topic of research. There have been some papers, for example, saying that if they are following Rossby wave trains, there's a good chance that we have teleconnected heat waves in regions that are important for food production, and that has been highlighted as one of the climate risks. If you look naively and just correlate, it's not very obvious that there is a strong correlation, but for example, the paper by Jerry Meal has shown that if you impose a heat wave on the Dust Bowl area in the US, so the Central Great Plains, which is also a big food production area, then you have both in a model and in correlations in observations a heat wave in Central and Eastern Europe, for example. So this is so there could be the wave train could be one reason why they could be correlated, but also El Nino causes very well-spaced events, and so if your heat wave is influenced by that, you will have a correlation. So it's important because we need to think about the vulnerability, for example, of our food system to heat. The food crops are sensitive to heat, particularly during their flowering phases. So they are also sense thresholds rather than changes in heat waves. So we need to think about it, but the jury is out, I think.
Great, thank you, Gabby, for the answer. Okay, we have a question that came to us via email. So, and this is for Professor Swadhin Behera. Considering regional model biases, how can accurate local predictions be ensured for effective climate adaptation?
Sorry, whom
Okay.
this to?
Sorry, yes. Yeah. Considering the biases, we understand there are biases for certain climate processes and climate phenomena. However, we know that some of the climate phenomena like ENSO, the Indian Ocean Dipole, they're more predictable with less biases. So we focus more on them and try to see how well we can, based on those predictions of ENSO and IOD, we try to teleconnect by using AI machine learning rather than directly using the model predictions for teleconnections. Because we find by using AI machine learning, we represent the teleconnections better, and we kind of reduce the biases in the teleconnections. So that way we try to reduce the biases. There are other ways people are using now AI machine learning to improve the ensemble mean by somehow reducing the biases. But they're less accurate than directly focusing on the phenomena like ENSO and IOD and their teleconnection using AI machine learning. Thank you.
Great, thank you, Swadhin. Okay, so the next question, it's related to some ocean atmospheric dynamics. So this one is for you, Shang-Ping, and it comes from Peter Best. And I think it's interesting because I actually don't know what atmospheric river is, so I hope you can enlighten us a little bit. But the question is, will atmospheric rivers become more important in impacts looking from the tropics to the poles? You're muted.
Yes, thank you for the question. So I do think atmosphere rivers are going to become more intense just because the warmer atmosphere can accommodate more water vapor. So the cautious Kaplan equation predicts water vapor saturated water vapor is going to increase in the atmosphere 7% per degree temperature increase. So I guess we have our climate system has warmed more than 1 degree Celsius compared to pre-industrial levels. So if we are on the still rising trajectory of carbon dioxide concentrations in atmosphere, we expect to see more water vapor in the extratropical cyclones, and those cyclones carry atmosphere rivers. And those atmosphere rivers, when encounter coastal mountains, they are going to the air is going to rise, and therefore the mountains are going to squeeze out the water vapor atmosphere rivers carry. So in other words, we expect to see more intense rainfall in flash flooding events on the slope of mountains where the atmosphere rivers come from to impinging upon. So this atmosphere river impacts, of course, are well documented on the west coast of the United States, but also especially during the winter rainy season. But the atmosphere rivers are also extremely important for summer rainfall in the East Asia region, where they're important mountain ranges. And in the past few years, actually, there were devastating kind of a unimaginable amount of rainfall, and breaking records in many parts of China during the summer. So the atmosphere rivers are not only a winter phenomenon, but also in monsoon regions could be devastating. During the summer monsoon season. So the short answer is yes. Those atmosphere rivers are going to become more intense, and therefore the risk for flash floodings on certain mountain slope regions are going to become more severe.
Great. Thanks, Shang-Ping. Okay, so the next question is for Swadhin first, and then anybody can also pitch in if they have anything to add. And it's from Didit Okta Pribadi. So how do we deal with the rising of megacities in monsoon areas? So there's this worry that there's a lot of cities being built where they might be affected in the future. So do any of you have any idea how we can deal with these factors? Swadhin, you first.
Yeah, okay. So probably my fellow panelists and speakers will have better ideas about that. I think the next IPCC report is focusing more on megacities and how the climate change is going to affect those megacities. I totally agree. The monsoon interaction with these megacities will be a challenge to understand and also to kind of develop mitigation measures. Especially for big cities like Mumbai in India, and with a big population, and there is a big pressure on the urbanization and its effect on how the rainwater drainage system works. So that's why when you have a slightly severe monsoon, most of the city gets flooded. And then on top of that, the sea level is rising. So the water over the land cannot be drained out to the sea easily in the future. So that will create a kind of double punch and will be a very challenging issue, not only for Mumbai, for many of the coastal cities which are affected by monsoon and which are increasing in population and the urbanization. Thank you.
Gabby, I believe you have something to add, so go ahead.
Yeah, we had a project in Edinburgh for flood risk with Kathmandu, which I have been following as an observer, and I found it very interesting. They developed an iterative method with city planners to first and with populations on where they wanted to grow and what they envisioned their city to develop like in the future, and then looked at the risk, because that development also influences the flood risk, of course, and where the floods are particularly occurring. And then they went, the scientists went away, Kathmandu people along with ours, and tried to figure out what does this mean for flood risk if you develop like this. And so it then fed back to the city planners and to the population that if they take this choice, this is where the flood risk will be particularly severe. So a process that involves not only what we understand scientifically about flood risk in a region, but also what particular development choices that the population might be interested in would mean. And I think this is a really nice way of bringing scientific knowledge to bear while considering what people are trying to find out.
Thank you. Matt, do you have anything that you would like to add, or can we move on to the next one? Okay. The next question is to you, Matt, and sorry, I muted myself. And it's from Ian Davis. How do we address the uncertainty of future UK climate, given your work and that of, for example, Van Western in 2004? Suggesting high risk of AMOC collapse. So I think it might be important to briefly explain what AMOC, or the Atlantic Meridional Overturning Circulation, is, and what this collapse might entail, not only for the UK, but apparently this seems to be, or could be, a huge issue for all Northern Europe. So yeah, if you have anything that you'd like to add, Matt.
So in the North Atlantic, we have cold, salty water sinking at high latitudes, and the Gulf Stream is actually part of the flow which is linking up with that at the surface, sinking and then returning to the equator at depth. And some models have been shown to under climate change scenarios to produce a slowing of this Atlantic Meridional Overturning Circulation, which would actually put a brake on the climate change signal that you see from the greenhouse gases. But in most of the scenarios, there's not a complete collapse. So I think the latest science on this is that a complete collapse of the AMOC system is not likely in the next few decades, or maybe even up to 100 years. That's not to say it can't happen longer in the future. But there's certainly, it could alleviate some of the initial impacts of greenhouse gases, but eventually the greenhouse gases win out. So, and I think it's actually contained in the scenarios that we have in the models. So this is something that is simulated and included in regional climate scenarios. So, yeah, I don't think it's a likely scenario, and in any case, it's already included in our projections.
Okay. Great, thank you. Well, since you have the mic on, let me just take the chance to ask this question, because we saw it in the chat, and I think that sometimes the audience might miss some of the questions that are in the chat. So this is from Susan Solomon, and it's regarding one of your slides, suggesting there is more time to mitigate when all models and their consistency with observed warming than might otherwise be thought. Can you please reconcile this with numerous recent papers arguing that we are almost out of the allowed cumulative carbon?
I'm sure Susan knows the answer to this question, really. She's one of the most famous climate scientists in the world. But my slide was really illustrative of the fact that if something that we call the climate sensitivity, so that is the warming for a doubling of CO2, if that is smaller than the models suggest, then it means that that we can emit more greenhouse gas before we cross a particular temperature threshold. I think that's a simple kind of physical argument. Now, the complexity comes when we include in our models feedbacks from vegetation, someone else mentioned that in the chat, and carbon cycle and ocean biogeochemistry, etc., and that allows you to do a complete calculation. So my slide was really illustrative of this idea that the climate sensitivity affects the point of crossing of various temperature thresholds, but you need to go to the literature which uses the full system models with the carbon cycle represented to get that allowable emissions. But certainly the results I've seen from those studies suggest that yes, we are getting close to burning up all the fossil fuels that we need to do to cross these particularly 1.5 degrees warming barrier.
Great, thank you for explaining that again for all of us that are not climate experts, and yeah, it was very good. So I'll move on and go to Shang-Ping next with one of our questions that we got from an email. Which interdisciplinary approach do you think are essential for building effective climate resilience frameworks?
Oh, that's a tough one. Yeah, I guess that let me just fall back to the earlier question about monsoon, the impact rising seas on the monsoon regions, right? So I guess in the part of Bangladesh that's facing the Bay of Bengal, that's a river delta region, right? So very low-lying land region with a huge population. I guess even these days, I guess when there's tropical cyclones that make landfall on that part of Bangladesh, it often cause a devastating impact on life and properties. And now we have a sea level rise, and on top of that, tropical cyclones, especially most intense tropical cyclones, are expected to become more frequent, and the wind speeds are going to be higher, and therefore the storm surges are going to be higher. So that means that region is already kind of suffering tropical cyclone impact. I think that the physical science is sending a message, that this is going to become even worse, right? So I guess it's not for somebody like me to kind of tell the people there what to do, but I think there are more experts kind of need to take this risk, increase the risk in already very high, region prone to storm surges. So they need, I guess, the city planners and engineers. They need to figure out a way to deal with this rapidly worsening situation, in order to mitigate disasters. So that is I guess a message from physical scientists like me. Yeah.
Okay, great. So we're almost running out of time. So I'll just gonna try a quick lightning questions for the panelists, and then we can wrap it up. So I have one here from just quickly get it. The question moved. So this one is for Gabi, and is it was here, but then he got okay. So this is from Mohammed Abdallah. Considering the regional differences in climate impacts highlighted in the article, what specific strategies do you recommend for effectively communicating these risks to local communities, especially those that are most vulnerable to climate change? And we can go to Gabi first, and then to the rest of the panelists, if you have anything to add.
That's a really tricky question and an important one. I think it needs to be an interactive conversation. So not just explaining what needs to be done, but also hearing what communities already do about extreme events, how they adapt, because there are lots of, there are also traditional adaptations, and so it's quite tricky. So there's a few interesting ideas hopping around. So for example, the climate hubs from the My Climate Risk Lighthouses are looking communicating with local scientists on what climate risks are and how to develop an accurate representation of local risks together with those local researchers. So that is one good way to go about it. In any case, it will be an interdisciplinary question of what is the risk to humans, to crops, and so on from extreme events and from flooding, and how can we deal with them. I think this might be one where maybe Matt or others have used too.
Yeah, I would just answer very quickly that we need scientists from all over the world to help us with this. So local scientists, particularly from the global south.
Great, thank you. And I guess we'll go to the final question before we wrap the meeting up. So this it's for Matt, and then everybody can pitch in, please. So it's from Hassan Jolahi. There are many conferences, forums, and meetings on climate change and its effects on health, quality of life, and on general the planet. But is it a guarantee for the implementation, or is there a guarantee for the implementation of their outcomes? What should international organizations do in this regard, I assume, to make sure that the things that are being discussed are being implemented to a certain degree?
Well, I perhaps would say, even though we highlighted some of the uncertainties in this presentation, that uncertainty is not necessarily a barrier to action. And I think that we know enough about the basics of climate change to be able to implement policies. We are scientists, not policymakers. But I think we can be confident in our science so that policymakers can make decisions.
Great. Gabriele?
Yeah, I completely agree. And for example, while I was agitating in my slide about small differences of what exactly the hottest day in a year looks like, all the models agree that it will be hotter. And all the models agree that there is a risk to human health and humid heat. So this is something we definitely need to highlight. We could also be in the same risk danger with sea level, for example, where we could agitate about the exact level of melting that is occurring in the major ice sheets. But meanwhile, thermal sea level rise just from ocean warming is progressing quite strongly and providing a lower limit. And on top of that, we can observe the increased melting, and with it the sea level rise. So we should highlight what we know, and we should have an adaptive strategy as we go into the future. And I think that's important for communities to see what is the most likely thing at this point, and but keep the options open for if it becomes worse or maybe not quite as bad.
Great. Shang-Ping, Swadhin, do you have anything that you want to add regarding to this?
Yeah, I totally agree with both Matt and Gaby, and I think there are some uncertainties, but we already know that it's happening. There might be some uncertainties on the severity of what is going to happen in the future, but the models are projecting well at this moment, and we should not deny those facts and deny the actions based on those things. Thank you.
Great, thank you. Okay, so we're unfortunately we're running out of time for today's discussion. So I would like to ask all of our panelists to leave us with one final takeaway message, either to the relevant scientific communities, to the relevant agencies, or to policymakers, because even if we're all scientists, we know that policymakers need all the help they can get with some feedback. So I'll start with Gabi first, and then we can move to the remaining panel. Any final thoughts? Yeah,
I think what we see clearly is that increasing climate change causes risks, and we cannot anticipate all these risks, and some of the possible outcomes could be very, very problematic. So when we are concerned about the costs of addressing climate change, we should be way more concerned, and I am way more concerned about the costs of not sufficiently addressing it.
Great, thank you. Shang-Ping?
Yeah, so I think recently we see in the news more and more record-breaking extreme events are taking place. For example, the 2023 was the hottest year on record, right? So and you have a warm sea surface temperature in various parts of the world. Not only not only the El Nino that kind of took place during the 2023 year. So, I guess the important thing is for our climate scientists to kind of understand and figure out a way to predict the various patterns of sea surface temperature. So this is a kind of in a sense, the current models are subject to tests, right, in terms of prediction, certain modes of sea surface temperature variations and their teleconnections, their impact on extreme events. So I guess in that sense, by watching or analyzing every move of our climate system, I think that's an important way, to contribute to society and also to identify the problems in the models and improve the models, and therefore its predictions and projections.
Great, thank you, Shang-Ping. Swadhin.
Yeah, thank you. Thank you for having me here. And it was very nice to discuss with all of my fellow panelists. And also we had good questions, great questions. I think we should have more opportunities to interact with the society, not only researchers, but everybody in the society. And kind of the climate science should evolve to make it more multidisciplinary, so interdisciplinary, transdisciplinary. So the health researcher, the social science scientists can also interact with climate scientists to develop adaptation mitigation measures. And in that way, I feel the new thing which is coming up now, the digital twinning technologies, we are thinking of developing so that anybody can use these digital twins to do case studies, what-if scenarios, and to understand the sensitivities. I think that will be nice to approach. Thank you.
Great, thank you. And the final words to Matt, who led the article that inspired this session. Matt, thank you.
So perhaps I'd say on behalf of all the authors of the paper and the panel members and those people who provide supporting articles, thank you very much for attending this webinar. We hope you've found it interesting. If you're just starting out in your career in climate science, please stick at it. We need the best minds in the world to solve this problem. I would say also it's an immensely interesting problem. I think understanding climate, although we've learned a lot, we've still got more to learn. It's probably on a par to understanding the human brain. So certainly plenty of interesting scientific questions to still answer. Thank you very much.
Great. Thanks, Matt. And thank you all for those final thoughts, and thank you to today's speakers and expert contributors. So Professor Mat Collins, Professor Gabriele Hegerl, Professor Shang-Ping Xie, and Professor Swadhin Behera. And thank you to everyone who joined us today. I hope you enjoy this session. For now, for me, our guests and the entire team at Frontiers, thank you once again, and goodbye.